Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
You really have to make them by hands, and it requires a lot of work. And abstract cryptography would, and is good for optimization. And abstract cryptography is already proven successful in finding attacks. So many protocols were found to be flawed just because people use formal methods, those abstract methods, and they found certain bugs and attacks on those protocols. And the open problems today is first, if we cannot find attack in this abstract model, have we proved anything? It's not really clear today, and we don't really know. And the second thing, really the big open question is we have to find really efficient procedures for deciding is there attack in this model or not. So there are some results that secrecy property is undecidable. And for very general class of protocols, the question is really, is this class really what is reasonable to expect from protocols to be? Can we find some smaller classes that will be decidable or maybe even very easy to decide? It's not quite clear yet. So our technical background is from behavioral theory of algorithms. So it's based on the work that Yuri and Gurevich and Blas pretty much did. And for different classes of algorithms, they were defined by some postulates and some complete languages for programming those classes of algorithms were given. And these are ASM thesis, and there are many flavors, depending on which class are we interested in. And there are a lot of results here. What we're going to use most for abstract cryptography, it turns out that we need very, very simple model. We're going to need only the small step algorithms, and the only interstep interaction that's going to be allowed is just going to be import from a background structure. So it's quite specific, a very, very specific model. It doesn't really require a lot of those later theses like interactive small steps and parallel or distributed. So a few words about abstract states. Machines, they're given by some set of postulates. And the first one is that the states of the algorithm, no matter how abstract it is, on its natural level of abstraction, they're always first-order structure of some fixed vocabulary. And as a computer scientist, you can always look at the structures as memory, some kind of generalized memory. You have some labels, some function symbols, and you have some number of parameters. And if you look in the structure is going to give you value for that location. And there are a couple of pretty much inessential technical choices that are made. All the Boolean and Boolean operations are in vocabulary. Vocabularies are purely functional structures, and we have the symbol and element undef in vocabulary in order to model partial functions. And what the algorithm does, the algorithm transforms states. So every algorithm has something called one-step state transformation. And the technical choice that was made was to have the algorithms can never change the carrier. And the reason behind it was that we can always pretend that whatever we needed in a later step, it was always there from the very beginning. And if we make that choice, we can express what is the difference between two states, previous and after an algorithm made a transformation. So we can just take a look at all of the locations, and we can see which one were changed. And we can define what is update state of the algorithm at some state. So you can, again, look at the structures as memories. You can take a look at the memory. You can see what locations were changed. And you can just read that what the algorithm does is changing some location with the new content. And this is called updates. The second postulate is isomorphism. And it says that all states associated to the algorithm are closed under isomorphism. And the intuition behind this is that really it's isomorphism type of the state. It doesn't really matter what the representation in concrete structures or states are. Whatever is relevant for the execution of an algorithm has to be represented explicitly in the vocabulary. I mean, it means like if you had the red integers and the green integers, then your algorithm made different calculation based, are you going to use red integers or green integers? It really means that it's not about integers, it's about something else. And also, I mean, initial states of the algorithm has to be closed under the isomorphism. The important thing is, because the algorithm has to respect that isomorphism type, that if we have two states that are isomorphic and the algorithm makes a step, that change, that step that was made also has to respect the same isomorphism. And the third thing is bounded work. So whatever the algorithm does in one step is something that is finite. And it's not even enough to require a tab that says it is finite. We really have to define what it means to make the finite work. And that finiteness will follow from different assumptions. I mean, for different kind of algorithms, we're going to have different reasons and different ways to express what it really means to execute one step. So here we come to the bounded exploration witness. The intuition is that whatever algorithm does in a state, it does by evaluating some terms. And based on that evaluation, it's going to compute the next step. So the reasoning is that whatever the algorithm does in two states, if all those terms have the same value, then the work must be the same. And that work is expressed as something that the algorithm changed in its state. And of course, we have different definitions of what the terms are and what the values of the terms are depending on the algorithms. In just non-interactive small step, it's just ground terms. You evaluate the ground terms. If you get whatever is the same, you're going to do the same step. If you have interactive, you're going to have also something called answer function that will give you some kind of interaction with the environment. If that environment reaction is the same and your state is the same in that way, your work is going to be the same. So again, non-interactive have ground terms, and interactive will have something called extend terms. One important thing that we're going to use is background structures. The background structures were first introduced more as a convenience than necessity. It was convenience for algorithm to pretend that when it creates the element, it doesn't have to create a pair of that element or the set of that element. It was convenient to pretend that everything was already in the state. It turned out with our case study of cryptographic protocols that it's really necessary to have background structure. You cannot even model the behavior of the algorithm in a way we want it without background structures. Because the algorithm would have to create things that are just not accessible to him. But with the use of background structure, we're going to solve that problem later. So the problem was how to create some fresh objects without having to create all those pairs lists and things related to it. So the idea was to create a background vocabulary to have all those symbols that are needed, pairs, projections, things for handling lists, sets, and whatever, and to define those elements on a set of something called atoms. So there was a unary predicate atomic that was saying which elements are just atomic and which structures, which elements are generated by the background vocabulary. So the definition of the background class was given in a paper by Blas and Gurevich, and it's also an isomorphic closed class that has certain properties. The first property is for every set of atoms, you can always find a structure in that class that has those atoms, that set has atoms. The second is that whatever is embedding of two sets between, that you can always extend that embedding of the sets into embedding of structures. So whenever you have two sets of atoms and there is embedding, you can always find some unique embedding of those structures. And the third one is that every element has an envelope, which means that whenever you have some element of the structure, you can always find the minimal structure in that background class, which is the smallest substructure of it. And okay, for some background class to be a background of vocabulary, we're going to do the following thing. We're going to require that all background functions are static. So the algorithm cannot change what is a set, what is a list, what is a pair. I mean, this is fixed forever. And we're going to require that if we just forget about all the functions that the algorithm is using for some internal states, and we forget about that, what we get is a structure that is from that background class. Now, we're going to call exposed elements that are in domain or codomain of some foreground functions. That means the algorithm really did some work with it already. So those elements will be already in some kind of sense used by the algorithm, and this you can notice that in a state. And the active part of the state is just the envelope of it. So all the lists, all the set, everything that you can build from those elements that are already used, this is the active part of the state. And the definition of reserve of a heap of the state, the elements that you can use, you can import, is just the atoms that are not in the active part of it. The main theorem is that every permutation of that reserve extends to unique isomorphism, and which is density on the active part. So the reasoning was that, in the motivation, that whatever element you pick from the reserve, it doesn't matter. What you get is always isomorphic. So the thing was, whatever you do by importing, as it should be completely irrelevant which element, which blank element you choose from that reserve, from that bag of the elements that are not used. And now we're getting a little bit closer. So the thing that we need and is pretty much use of ASM thesis in cryptography. And this is kind of negative use of the theory. And so far the theory was used pretty much only for positive purposes, for modeling of systems, for testing, for proofs of correctness proof. Pretty much the theory was always used in a positive way, which is kind of like unlike what the Church-Turing thesis was used. It was primarily used for negative purposes, to proving that certain things are impossible. I mean, proving that something is decidable is kind of result, but it doesn't really buy you much. And the question that we ask ourselves is, can we really use that theory for the negative purposes? And of course, our application in security was pretty much the natural thing. I mean, we want to reason about, can algorithm do certain things or not? And our result, the main result that we are trying to do is algorithm cannot do something. So before we go into the direction of really using this for negative purpose, we need to develop some machinery for it. And a lot of those things were scattered around the ASM literature, but they were not really ever put in one place. So we're going to define a couple of notions on the structures first, as a static things, and we're going to define certain notions on states of the algorithm. And we're going to try to relate those things. We're going to try to connect what the algorithm can do with something that we can just calculate from the state. So we have the element of the state is accessible if it's a value of some term. That's a pretty standard thing. And we also have definition of similarity between those two structures. So if the two structures are induce the same equality relation on terms, then they are called similar. It's different than isomorphic. I mean, this only means that the part that is accessible to you looks the same to you. You don't really know what is beneath, what's the interpretation, all the functions are just not accessible to you by terms. And of course, we're going to use a little bit extended terms and similarity for extended terms when we're going to deal with interactive algorithms. We're going to have not just state, we're going to also have answer functions. And not just any answer function. We're going to have answer function that is only importing from the background, which is a very special case. And now we're going to talk about a little bit some notions on the state. So state reachability is pretty obvious. I mean, you can reach state y from x. There's some algorithm that has transformation that allows you to go from x to y. And the term and notion that we introduce is distinguishability. But it's really quite a standard thing. You say that after an algorithm, make one step, and if it was in a state x, it's going to know that. So you find some term, you evaluate some term in the next state, and you have a true, you know you're in the next state. You were in the next state. So this is the definition of distinguishability. And of course, indistinguishability. There is no such algorithm, which is what we really need. And the basic result was relating those notions. So it's still unpublished paper, but probably going to publish it soon. So indistinguishability is equal to similarity. And reachability, you have to, of course, you have to have update set finite. You have to have all the elements in the update set finite. If you have the same carrier set, then the state is reachable. There is some algorithm that can calculate that. And of course, different classes of algorithms are going to have different classes of terms because similarity is defined for different classes of terms. Okay, the difference between two states is finite. In terms of update set.
Because if the difference is on the accessible part.
Okay, is finite and accessible. Every element in the update set is accessible. Okay, maybe I should write a little bit clearer. Okay, you have to have everything accessible, of course. If the update set is finite and everything in it is accessible by a term, whatever the term is, and the carrier set is the same, then there's an algorithm.
So this is a case when there is no interaction.
In interaction, it's the same, just this different definition of terms and accessibility. You have to have accessibility by not just a state, and the answer function. Yes. And yes, like I said, different classes of algorithms have different classes of matching terms. So non-interactive small step algorithm is just going to be ground terms. And if we're going to have ordinary interactive case, which we also studied, you're going to have extended terms. Terms that you just don't evaluate only in a state, you also need some answer function. And there's also some generalization of depending on a set of answer functions that you think are possible. Not just the point of view from what the context is, just the point of view what you as a system designer think the environment could possibly output. So it's not, you restrict those things, not even everything from the background. And this is pretty much our toolbox for establishing those negative results. I mean, now we know what the algorithms cannot do, and we know how to test that thing in a state. We have the static notions that we can just evaluate in a state without really thinking about how many steps we have to do things like that. And now we come to the application. So it's abstract model of cryptography from the ASM point of view. So whatever the agents are, we're going to say the agents are ordinary interactive small step algorithms. The only interaction allowed, intra-step interaction allowed, is going to be import from the reserve, from an appropriate background. And that background is going to depend on a choice of cryptography that it's going to use. Public key, shared key, hashes, whatever. Honest agents are simple. I mean, it's not very difficult to program what the agents do. The honest one, it's very, very easy. But the problem is what the intruder can do. And the point of our model that we're trying to make is we're trying to make the intruder that can do whatever the small step algorithm can do with this kind of interaction. And things that are pretty much don't really exist today in abstract models of cryptography is that you have natural notions for certain things, let's say indistinguishability. You cannot really say that in any formalism today, really used. You cannot say that two states of the algorithms are indistinguishable. Accessibility, of course, you have. It's kind of secrecy that's normally used. Can you access some subject of some encryption? And state reachability is basically what most of those formalism are focused And I'll give you some idea how the computational cryptography model looks like on a very simple model, and I'll show you how to relate that abstract model with the computational one. And actually, we got that result for free. So symmetric encryption scheme is a triple of algorithms. So the algorithm K is algorithm that given some parameter like key length and tosses some coins and outputs some key. You can use that key for encrypting some strings, also flipping some coins, and you would get some ciphertext. And you can also use that key to get the plain text from the certain strings, not all. And what is always needed for every encryption scheme is that decryption and encryptions are inverse operations. So if you use the same key for encryption, you can always decrypt that with probability 1. But doesn't really mean that this is secure. Security is always expressed in terms of probabilistic polytime algorithms, and there are many notions of security in probabilistic cryptography. I mean, many. And one of the tasks is for us to find something that is abstractly sound from the computational model, but it's also, we have to find which computational model we can really represent in abstract cryptography. It's not really clear yet. We have some ideas, but this is still open question. So if we have that algorithm and we have pairing, we can induce ensembles on strings. For example, we can take the key algorithm, key generation algorithm, give it some parameter of key length, flip some coin, generate the key, and encrypt 1. And we can make a pair of that and, let's say, bit 0. And we have definition of indistinguishability by probabilistic polytime algorithm as a function of that parameters. So let's say
the dots are
coins.
set for the coins.
Yeah, this is for flipping the coins. It's a key length parameter. So all those algorithms.
Parameter.
Yeah.
And then ensemble is a family of probability distribution parameter, as you say 1024 bits.
Okay, and depending on the type of those algorithms, on those encryption schemes, you can have that those two ensembles are indistinguishable. Their definition of computational security that would make those two ensembles indistinguishable. So on the left side, we just have encryption of 1, and on the right side, we have encryption of a pair, 0 and 1. And if you're just giving that string from that ensemble, you cannot really tell where you are. So those two ensembles are not indistinguishable because you're going to get a key, and with that key, you can go into encryption, decrypt it. With the decryption algorithm, you're going to find out that in uppercase, you had encryption on 1, and down, you had encryption of a pair of bits. So you can really distinguish those things in polynomial time. So the main idea is really abstraction. We're going to abstract from this parameter. Whatever is unlikely is going to become impossible. And whatever is a string, which is something complex, is just going to be element of abstract carrier. We will not really make any difference on the strings. We just make everything is different. It's represented by one element of a carrier in a state. We just move on. And again, we're going to use background structures. And I'll show later it's really necessary for creation in public key case. That was the main motivation. For symmetric case, you could actually get by without it, but it would be not very elegant and not very convenient. But in public key case, you cannot really do without it. So after thinking about 5 minutes about that example, it's very easy to make first simple abstract model. So if you have both key and an encryption, you just put in a structure what the decryption of that is. If you don't have both things, you have the encryption in your base set, but it's undefined. The decryption of it is just undefined. And this is those encryptions that are not understood are just viewed as black boxes. And what you get for free is theorem by Body-Rogaway from 2000. Indistinguishability of those two states implies computational indistinguishability. The way they defined it was not very easy because they had two different languages and they had to replace all the encryption with something called black box, and they had to define some permutation of keys to get the same expressions. But that was nothing but the definition of this isomorphism. They would really represent their expression with two expressions that are isomorphic to one each other. So if you do like this, after 5 minutes of thinking, you really get the model that is computationally sound with that respect. But there are two problems with it. The first one is learning by interaction. Let's say that you make some step, you get some new message, and you learn what some new key is. You have serious problems because now those black boxes can be decrypted. So whatever your environment gave you as a key, it also has to update your structure to has all those decryption now. Somebody has to do all that work. And it's not really clear how much that work is. I mean, it's intelligent work. You have to go and look what you can decrypt now, and you can see, can you learn some new key and decrypt with that new key? So it's quite a complicated process, not really elegant. And the second thing is reachability of states in the public key case. So this is the problem. So let's say you have a message, you have a public key, and you should be able to create encryption of it. But in order to create encryption, you have to put decrypt in the update state. And decrypt with not just any location, decrypt with a private key. Otherwise, it doesn't work. But you don't have access to private key. I mean, if you have the access to private key, the whole model collapses. And our solution was to use the background structures. To make it a little bit more clear, I'll give you one simple example how it really works. So let's say you have two states. One is S, one is T. In S state, you have encryption of a pair. And in T, you have encryption of bit 1. At first state, in S and T, they don't know what the key is, but later on, they learn it. Vocabulary, you use some function F, nullary, and G. You need decrypt, first, second, and everything that is normally used in ASM states. All the Boolean functions and everything else. And the base set has the bits, has encryption, has a key, has a pair, and again, everything that goes with the ASM state. So in the interpretation in both those states, in both S and T, the function F is evaluated to encryption E. And that's pretty much it. There's nothing else is defined. All the crypts, all the pairs, and nothing is defined. So if environment wants to give you key K on the input, let's say as a value of the function G, it not only has to give you that key, it also has to calculate all the logical consequences. It has to calculate what you could decrypt now. Now you can decrypt encryption with the key K, and in state S you would get P, and in state T you would get something like bit 1. And after you get that pair, you also have to calculate what you can do with it. So you can do projection, and the one left side is going to be 1, on the right side is going to be 0. You really have to account for all the logical consequences. This is complicated. Now I'm going to define what the background for symmetric encryption would be. It's pretty much simple. I mean, whatever we define in computational model, we just take the security parameter out, and that's it. But not quite. Those things were defined on strings, but now we have just messages. Messages is some kind of union of those three codomains. So these three functions, this is just some elements of the base state. We don't really know what their structure is. They're just elements of the base set. And we said that base set is freely generated by the both functions, which means their functions are injective, which means they're pairwise disjoint. So you would generate with coins all the keys that you can generate from those coins. You can generate all pairs of the messages, and with a given key and a message, by flipping the coins, you generate all the encryption. So there are infinite number of encryption for every key and subject. There's infinite number of keys. And that's not enough. We have to put projections on the pairs, and we have to put decryption. And those three functions will be undefined anywhere else. So if you have a proper key and you have a proper encryption, you're going to be able to decrypt and see what the subject is. So again, this example, we still have these two encryptions. We have the same vocabulary. We have the same base set. Nothing changed. But now we have different interpretations. In those function S before, we only had this interpretation of the function f is some element of a base set, and that's some kind of encryption. But now we also have decryption of it. We have the projections and everything. Those things are not reachable to us. It's not accessible. I mean, we cannot really access what the decryption of encryption is without the key. But it's still in the structure. It's already there. And the same thing for T. So those two structures are by no means isomorphic. But they're similar. But for all the values of all terms, all ground terms, those two things are similar. They're also similar if we have extended terms and we only have import from the background structure. You cannot really learn anything for the old encryption by creating a new one. That's not so easy to see, but it holds. And now, if the environment gives us a key, the only thing the environment has to do is only has to give us a key. It doesn't have to calculate everything that is logically entails from that. So now we don't have to create all the differences between two states. We just have to give the new information, and we're going to discover, and the algorithm will discover everything by itself. And we get the Soundness results for free, or really for free. So indistinguishability by small step algorithms is equal to similarity by ground terms now, again. And this is computational indistinguishability by a body Rodaway. Nothing to do about it. It's already proven. It's only a study of abstraction, a study of what they did in their proof in a little bit complicated way because the machinery was too ad hoc and they really didn't have a good means of talking about the quality of expressions. And the natural notion was real similarity. But you cannot really say that without having the first order structures as background. Another thing is state reachability. Now we finally have that property that we wanted to. We're still not sure, is it too strong for computational cryptography or not? There are not really results in that area. We're working on it. But the small step algorithm can create an encryption if and only if it has both subject and an encryption key, which is what we think about encryption, what it should be. It's not really clear, is this too strong for computational interpretation, for the proofs that something is impossible. Okay, and this pretty much brings us to the final part of the talk, and it's about practical implementation, use of all this theory. So we're going to use SpecExplorer, which is a general purpose tool for specification and testing. And our goal would be to have fast way for prototyping protocols. So we're not really interested too much about proving security right now. We are more concerned about finding attacks and finding them really fast. So we want to find all the errors in the protocol before we really start, usually a pretty elaborate process of proving security. And what we have is we have a complete decision procedure for the bounded number of roles. So given some bound of how many roles can be used in the protocols, we can let the SpecExplorer decide is there an attack in abstract model or not to it for some class of protocols, but very reasonable one. It excludes protocols which receive an encryption and then forward it blindly, which is not very realistic and is always questionable what it really does in computational model. I mean, the computational scheme usually break if you just encrypt things that you shouldn't. So these kind of things are computationally questionable anyway, and we just excluded that from the first model. Okay, so the way it works, if you have the honest agent, and which is executing some protocols, some ASM program, this agent accepts infinite number of input messages. At least everything that is isomorphic to one message is going to be acceptable. Intruder can also generate infinite number of messages. Not just isomorphic. I mean, you have some kind of knowledge, you can create all the encryption using it. I mean, that's infinite number. But what we are really interested in is intersection of those two sets. But again, still infinite.
messages out of an infinite set of messages?
No, it has a finite, let's say it has a finite number of keys. You can generate infinite number of messages with it. Just encrypt every key with every key. Yes, potentially. Okay, potentially. Okay, I'm sorry. So it can generate some finite number out of infinite number of messages. Okay. And again, those intersections also infinite. But the trick, and this is pretty much just reuse of the proof of ASM thesis, was that if you're really careful what you're doing, you can express this infinite number of messages with just a finite set of terms. There are not really that many different messages. The only couple of them count. Everything else is isomorphic, similar, something to it. So the way it works at initialization phase in a SpecExplorer, you would create some number of honest and corrupted agents. And you would create some kind of number of roles randomly. You just let SpecExplorer pick up everything for you. And SpecExplorer pretty much picks up every combinations. So intruder would ask each role. Intruder would say, look, this is my knowledge. This is what I have accessible. Please give me the representative of all those possible messages. So the role really makes the calculation of what can intruder could give it to me so I would pass. And calculates all those terms and give one representative to the intruder. And then it's SpecExplorer again. It has the set of possible parameters and just takes everyone. Runs in parallel. All possible roles, all possible input values. And this is all finite things because we have bound on a number of roles, we have bound on a number of messages. If the protocol guarantee is violated, we just stop the search. And we display trace of the run that caused that. And if no more move is possible, you get big, nice graph, SpecExplorer exits, and you know there is no attack with that many roles because the procedure is complete. And yeah, I could show it's quite fast. So you're going to start it now. It's going to search a little bit. And here it is. I don't know how much you see it. Okay. So, as you can see in those states, I mean, this is just many states combined in one because the graph is too big. So I'm just looking how many roles are really run and things like that. And the protocol, the SpecExplorer, would first create the agents. It would create some responder. It would create some initiator. And then it would start to either initiate the roles or just to run responder roles. And after a few steps, init, run roll, you would get into the state where the check is where the guarantee is failed.
Now, when you say run roll, which roll?
All roles.
All.
Yeah, I mean, okay. In one step, you run only one. You run one by one. But of course, SpecExplorer runs everything in parallel. But it has transitions in many states. But in one state, you only run one role. So you always have interleaving. So there is one action of the role. You have some calculation by intruder. Again, some calculation intruder, what's output, what's input. And then again, run on the role. So every step is just, you get one role that is run by some message. And SpecExplorer does everything in parallel. And because this is parallel, it's a lot, so I'm just trying not to make huge graphs. And if yes, it's exploration. Just it's a forward chaining. It's there was some work done in this area in symbolic trace analysis, and pretty much this is what it is. But I mean, I get it here for free. I mean, SpecExplorer just does all the ugly work for me. I only have to specify what the set of possible messages are, and then pretty much everything else is done by the tool. So what you would get here is this Love's attack on an Ethan Shredder protocol. I don't know how much you're familiar with it, but this is basically the trace on it. I don't know, maybe I should write it. Okay, maybe I should explain how it works. So you have two agents, and they're going to exchange some messages. Okay. blue maybe. Okay, so the protocol goes like this. The first message is there's some initiator called Alice and wants to talk with Bob. And sends a message saying, I'm Alice. This is some fresh value that I just generated, something called nonce, which cannot be guessed by any attacker unless it really has access to it. And I'm going to crypt this with the public key of Bob and send it to Bob.
What's the glossary? Who is Alice here?
Alice is initiator, and it has a key 0, I guess.
Key 0, so Alice is off of key 0.
Yes. Okay, we're just going to use, okay, this is either name or just public key for simplicity. If it's a name, you can look it up what the public key what the public key is for it, or in modeling of protocol, the easiest thing is just to send the public key. So the Alice would send its public key, some nonce, and would encrypt it with the public key of Bob. Send it to Bob. And the Bob would respond.
Of key 2.
Okay, the Bob here would be key 1. Yes, because here Alice wants to talk to someone called Alice. I'll show the attack later. And Alice would decrypt this message with the private key it has. It would look up, is this value the same as this value? And if it is, it would just return N to Bob. And Bob, again, here would decrypt, would check, is this the same thing as I sent? If it is, I'm fine. And the goal of the protocol is that if A is in this state, then A knows there is a B in this state, and that B talks to A and has exchanged N1 and N2 with it. So B already knows here what the N1, N2, and A is. So this is one guarantee. Another one is B in this state knows there is A that thinks it's talking to B and has exchanged N1 and N2. So both sides have some kind of guarantee what would happen. And I'm going to do a little bit more Blackboard, so I'm going to delete this. So the tag that was found by Love is this. A wants to talk with something called E. And E is dishonest. So this is intruder. And it would set, again, A, N1, encrypted with the E. But because E is dishonest, does not want to follow the protocol, we'll do something with the message and send it to B. So it would say, A wants to talk to you. You can do that because you can decrypt this and create a new one. The B is public key, everybody knows that, and private key is here. And the B will say, oh, great, I want to talk to A as well. And it will say N1, N2, encrypted with A. Now, E cannot decrypt this message, but doesn't care. Just forward it. And A say, okay, fine with me. Now, E gets to see N2, which was originally sent to A. Recrypts it again and send it to B. Now, the guarantee for A is broken, obviously. But it's broken because E is dishonest, does not follow protocol. So there's really no guarantees whatsoever. But the problem here is that in this state, B thinks there is A, that thinks it's talking to B, and has exchanged those two things. But that's just not true. So this is what it finds. It checks all those guarantees. So it's saying if this person is honest, I'm going to check the guarantee. If this person is dishonest, I will disregard the guarantee. And here is A is 0, Alice is 2. No, Alice is... No. Okay. Alice is 0, Eve is 2, and Bob is 1. And this N7 is 1, and N16 is N2.
And the guarantee is given annotation.
Yes,
Like we
like formula. Yes. So basically, in every protocol, you have some guarantees that are attached to it. And it's usually say that if A is honest, and I don't know, B is honest, and B completes the protocol, then there is a role that has those parameters in it. Of course, only if they're honest. Sometimes honesty of...
Sometimes
is,
even stronger things in the two.
yes.
Only if it suffices that your opponent is honest when you get your guarantee.
Yes. I mean, sometimes, but this is good enough. I mean, guarantee for you if you're not honest, but that doesn't really make much difference. So depends. And you can have, I don't know, unique role. There's only one. Things like that. So those kind of formulas are what you're trying to check after running a protocol. And if this is violated, you just exit. And proving that, I don't know, for 2 roles, this modified protocol is secure would take a few minutes with the SpecExplorer. So you know there are no attacks with 2 roles. And most of the attacks are really not that big, so it's not something that you cannot really just try. I mean, once you have this running, it's pretty... It's not complete in the sense that you can really decide security of the protocol, but after you try it with a couple of roles, you know you're off. I mean, if it's good enough, it's good enough for a few roles. There are some results saying, some theorems saying that if there is attack, there is only attack with not that many roles, but they're not too confident. I mean, at least I'm not too confident about their results.
The nodes of the graph you see are hyperstates. They represent several states. How many states do we have really?
Wait, before you leave, I want to connect so we have a real expert here. Josh?
I think so.
Okay. Okay, here we have 37. I mean, of course, because it's...
We have the second to none. So I think
yes.
because I'm not sure if we always say that was over his head.
Yeah, I mean, it was fast, but... Yes, I know.
It would be interesting to try it.
I mean, the thing is, the first step that we did is really look into these results from Abadi-Rogaway and try to interpret that in context of abstract state machines. And once you see what they've done and what they have as a result, it turns out that it's simple. I mean, it's just what a small step algorithm can do. Nothing more than that. And it looks like a really quite good model to start working. This result with testing, it's extremely difficult to prove that you only have to check finite number of messages in some format and how. But if you're working in the context of ASM thesis, I mean, you have most of those things already proven. You just have to reuse those proofs. It's much easier once you have this technical background, I think, for analysis. And those cryptography related results right now. We just imported it. I mean, we have the theorem. We see what this formalism is and what the formalism should be. Everything else we just inherit. So this result was not mine. We just inherited. But the way it was defined, it was terrible. I mean, you have two expressions. Then from two expressions, you have to calculate all the keys that are accessible. Then you have to replace all the things in initial expression with the black boxes. Each black box is a different. And then you have to find the permutation of the key letters for those two things to be the same. But that's similarity, which is much easier to define and much easier to check. I think we're done.
We made one abstraction that they believe that you can never guess it. The abstraction we made. Essentially, what we call it. You guess a string, so here we take the limit. Don't know where it was. So this is one abstraction. You cannot possibly guess the long run of things. Maybe it's an abstract.
Yes.
So this was a simplification.
Yes.
But the rest was really not very important. It had calculus.
I think it's. I think once you have a good relation, once you have a good relation about what is abstractly sound.
That's what I want to say. This is, I agree completely. This is cleaning up.
Yes.
Yes, because what they have to do is this encryption that one has but doesn't understand, cannot agree. They have to represent it with an extra element, box.
I just want to say that these people who Jan and Novak group, it's not a kind of small group somewhere. This is a top people that can reach with the same qualification. But can get to one. I think it's really good.
As a logic, it's very hard to work with because of course this box is not equal to itself. There is one thing which in fact can represent all the things that you don't understand.
Yeah, they were on the wrong structure.
Yes, I think so.
I think this is what is supposed to be presented in a forum where it's accessible.
Working on it right now. I mean, once you have this framework done, it's there are a lot of ideas how you can really search for procedures and how to really decide or find an attack, because everything is clean now. I mean, you program things in a way you're used to. I mean, anybody that's ever did some programming, it's very easy to see, can I program something like this or not? It's much more easier than trying to prove some property or some ad hoc formalism, which you just have to study and study until you really understand what it is. And for me, this is a very natural way of just thinking about things. I mean, this attack was took me about 1 week to figure out this and to write these tests all together and make it run. Because it's programming. I mean, it's something that we are all used to do.
There's another field of logic of knowledge explanation.
Yes.
The problem there is the explanation they give. There is this omniscience. So if you learn something, you also learn all the consequences, which is absolutely impossible.
Yes, sir.
The background may help us solve this problem.
We did think about something. I mean, once you have distinguishability as a notion on any structure, you have logical knowledge for free. I mean, this is a well-studied thing. The only question is, what is the relation? So you can define what is the knowledge of the algorithm easily. Yeah. Okay.